Yes, perfect.
Full screen.
Congratulations.
Okay, this is very good international cooperation for IT. We can put some people on the moon. We can figure this out. Okay, so I start this presentation then, and we have 1 hour, so I'll try to finish a little early for questions. So thank you again to Julia and Javier for coordinating this. I'm going to talk to you about this incredible international science project called the James Webb Space Telescope. It was launched on Christmas Day a few years ago, early in the morning, from Kourou, French Guiana, and it's working just perfectly now at the Lagrange 2 point. It's quite a bit of distance from the Earth, 1.2 million kilometers, and we are extremely excited because we are making very nice discoveries all the time now, some of which I will tell you about. There is a lot of competition to use this wonderful space telescope. We get 10 proposals and accept only one, and many hundreds. So I'll just tell you what we're looking at in case people are not familiar. The big gold colored mirror is the primary mirror of the telescope. This is an infrared telescope. Now it's in orbit, of course, in space. It's completely dark. You cannot see this beautiful gold coated mirror because we want it to be dark and cold. The secondary mirror is on the left side in the picture, and the light comes to the primary, reflected to the secondary, back through the middle to the science instruments at the back. That is the integrated science instrument module on the back. You can just barely see it. And of course, we have this wonderful sun shield, 6 different layers, the size of a tennis court, which has unfolded correctly. We were very worried about that. This provides the shade and keeps the telescope very cold for the observations that we need to make. So how did this talk come about today? Well, I was very lucky to attend this United Nations conference in Vienna, Austria in December. Space for Our Common Future, that was the title. It was really a precursor to the UN General Assembly meeting in New York, the Summit of the Future, coming up very soon this fall. And at that time, the United Nations as a whole will talk about how we can use space to help achieve the 17 Sustainable Development Goals. This is, of course, of interest to everybody on the planet. What does space science have to do with all of this? Well, I would like to argue that we can use space science as a tool to achieve many broader goals, including these goals of the United Nations. So it is a very important subject, and I congratulate all of you for studying it. Why is this important? Well, of course, we like to answer the biggest questions ever. Where did we come from? How did we get here? And are we alone in the universe? And you can see in this picture of galaxies from the Hubble Space Telescope deep field, a number of other interesting objects. By the way, everything in this picture that you're looking at is a galaxy, with the exception of one star below the second set of words. You can always tell in a deep field image what's a star in a galaxy by the diffraction pattern. But in the background are the more interesting objects, these tiny red dots. We call them the interesting red dots. These are the farthest and oldest things that we can see with the Hubble Space Telescope. And we were very interested to find out about these, maybe the first stars and the first galaxies that ever came into being in the universe. Well, we could not do it with the Hubble Space Telescope. We had to design a bigger telescope and better telescope. But how do we come to this point? I'm sure many of you will study this in detail as a specialized practitioners. You know, of course, today we can observe what's called the cosmic microwave background radiation. I'm sure this is old news to many of you, but I give it from the layperson's perspective. What is that? That is the leftover radiation from the Big Bang when the universe started. If you tune your radio in between the stations, you'll hear some static, which is in part this background radiation. But this is what we have as evidence of the Big Bang. For many years, I guess even today, there is a theory that the universe started in an infinitesimally small point called the Big Bang. And it expanded very quickly. It was completely silent, unlike the movies, completely silent and completely dark. There were no stars, there was no light, and no sound, of course. But eventually, the first stars and galaxies formed. This was because of differences in the radiation from the start of the universe. If it was all the same, we wouldn't be here today. But there were tiny differences in density and tiny differences in temperature in the regions of the early universe. And those eventually became stars and galaxies, the first ones. Our sun is not a first generation star. More on that in a minute. Eventually, the first stars and galaxies exploded in supernovae. We had second and third generation stars. The process repeated. And eventually, we produced from the original hydrogen and helium the more heavy elements, all the interesting ones. And these eventually condensed in other places to form solar systems, including our own. They formed planets, plants, animals, people, and at the pinnacle of evolution, astrophysicists. This last term, of course, I changed depending on the audience. But we are interested to find the first stars and galaxies that existed in the universe. And that was the main topic of this project when it got started in the mid-1990s, late 1990s. At that time, that was the only subject for the telescope. And when I had astronomy as an undergraduate student in the 1980s, long ago, we did not know about any other planets outside the solar system. Now we know there are thousands of planets around many stars. In fact, we think almost every star has a set of planets. This is a revolution in human understanding. But we designed and built this telescope to study these two main topics. Telescopes are very interesting, of course. Whenever human beings build a new telescope, we find some interesting things, and many interesting things we had not even thought about. Galileo, of course, was a very famous operator of a telescope. He was not the first to make it, but he was the first to turn it to the heavens and look at changes in the universe. Just last week, I was at the Jet Propulsion Laboratory in California to see the Europa Clipper spacecraft, which is launching in October this year. Will go to the moon of Jupiter, one of the Galilean satellites. In a few hundred years, we have gone from small sketches of tiny moons orbiting Jupiter from Galileo to visiting just a few tens of kilometers above the surface of this moon. Of course, there have been many telescopes, famous telescopes over the years. This is a picture of Galileo's telescope, which I saw at the Philadelphia Museum of Science and Industry when it was on loan. Very small, nondescript, but of incredible importance. This is the famous Hale telescope with a large glass, heavy mirror on the ground. This is a picture of one of the primary mirrors for the Hubble Space Telescope, which is now operating successfully many years in low Earth orbit. Of course, you know, we had some problems with the mirror fabrication, and we went with astronauts on several space shuttle missions to repair and fix the error in this mirror production. If you come to Washington, D.C. and go to the Air and Space Museum, you will see a copy the second mirror that we made for Hubble Space Telescope. We made two. Unfortunately, the incorrect one is on the telescope, and the perfect one is in the museum. But we learned from that experience to test our telescopes very, very carefully before they are launched into space. Here, for comparison, is the difference in size between the James Webb Space Telescope primary mirror and Hubble's mirror. James Webb is quite a bit bigger, but the most incredible technology is it's super lightweight. And that's what made the whole project work. If it was a solid mirror, it would be extremely heavy and we could not have launched it. These are some interesting telescopes, but as you know, and not too far from where you are, there are many state-of-the-art ground-based telescopes which are coming online in the next few years, including the Giant Magellan Telescope, the European Extremely Large Telescope, and some others. So telescopes are important. Galileo's was made in 1609. The Hale telescope mirror in 1948. The Hubble telescope mirror in the early 1990s. And then finally, James Webb Space Telescope in 2021. So let me, as a lawyer, just tell you a little bit about some of the important aspects of this program. I will not cover each of these bullets, but just to note that when the project was announced, it was supposed to be an 8-meter diameter mirror and a cost of $500 million. It took us 30 years to work through all the developments and launch this telescope, and it wound up costing quite a bit more than that. The US contribution is $9 billion. That's a lot of money. But in the scheme of things, the world worries about not too much. We spend almost that amount in a few weeks in our foreign military operations. The most interesting thing for me, the success of this program, is it is an international program. It involves the United States, of course, but also the European Space Agency, the Canadian Space Agency, and some others. And this cooperation was done through international agreements. Why does it cost so much? You might ask. It's a legitimate question. And the answer is, it's not like buying a car. If something happens with your car, you take it to get it fixed. Very easy to get to, and you can make many visits to fix it. But it's not true with the Space Telescope. It has to be almost perfect when you launch it and for the life of the telescope. Well, this adds to the cost. This was considered a very high priority internationally of the science community. In this country, it was the highest priority of the National Academy's decadal survey, 2 times over 20 years. And as I mentioned, it is a miracle of technology. The scientists are the beneficiary of incredible work by our engineers and technicians to build this instrument and deploy it in space. The key aspects are it is a lightweight structure and it's extremely smooth. The mirror is extremely smooth. We had, prior to the launch of the telescope, anticipated 344 things if they went wrong, such as the secondary mirror does not deploy, or the side panels do not deploy, or the sunshade does not come out, etc., etc. 344 of these, if any one had not worked, it would have been a failure, and that would have been a disaster. They all worked. It's a miracle, as I sit here today, that they all worked. But here is a picture of your presenter in our clean room at the Goddard Space Flight Center in Greenbelt, Maryland, in front of the Integrated Science Instrument Module, probably 15 years ago when it was being put together. That is very interesting technology, which houses our 4 instruments, carbon fiber composite. I will not talk in detail about the instruments today. We don't have time, but each one of these instruments is a marvel of engineering. The near-infrared camera from the University of Arizona, near-infrared spectrograph contributed by ESA and my center, our mid-infrared instrument, also by ESA and JPL, and the fine guidance sensor. These are all a near-infrared imager. These are all contained in that package behind me in the picture. Here it is being tested. And the wonderful thing about the design of this telescope with the sun shield is it is a miracle of contrast. It is exceptionally cold on the instrument side of the telescope. On the cold side, minus 233 Celsius, and the hot side, 85 degrees Celsius, quite a temperature difference. And you know, in most of modern life, with such extreme temperature changes, you also have changes in shape. And we had to make sure that the telescope structure would not change shape down to billionths of a meter, nanometers. This project has been in the works for a long time. Here is a copy of the front page of the contract that I reviewed before we issued it to our main contractor, Northrop Grumman, for the start in 2002. And since that time, we have had 300 modifications to this contract, many to look at, a lot of work for lawyers, but thankfully, no significant legal problems over the life of this project. That is quite remarkable. As I mentioned, it's an international agreement, and all future important space science projects, even ground-based projects, are benefiting from international participation. We need each other's resources around the world. And somebody said as a joke, it's also harder to cancel your project if you have all these international contributors. I mentioned something interesting about the main agreement that we have with the European Space Agency. NASA signed this agreement under what we call the Other Transactions Authority. It's not a contract, it's an agreement. And there are no exchange of funds between ESA and NASA. What ESA contributes to this arrangement was the launch of the telescope on the Ariane 5 from French Guiana, standard launch services. Our agreement says ESA must use reasonable efforts to put the telescope at the Lagrange 2 point, which from the legal perspective is slightly different than best efforts. Best efforts means if something goes wrong, you have to replace it. That was, of course, not possible here. It's a unique instrument, priceless, really. And what did NASA contribute? In return, 15% of all the observing time is provided to ESA. I'll skip some of the other topics, but the main important part of this handshake agreement does not involve any money between the two main entities. We're each contributing an exceptional thing that we do well from our own side. It is really the poster child for international science agreements. This Other Transactions Authority, which I have quoted here, is the language at the end of the legislation that set up NASA in 1958. And you can see on the bottom right picture, a very young guy I hardly recognize, next to Mr. Paul Demling, the author of this legislation, which created NASA. And it was his genius to include at the end of this language, this little phrase: we can do contracts, leases, cooperative agreements, or any other transactions as may be necessary. And that is the basis for all of these international cooperative agreements. Because we are not a contract, we don't have to follow the federal regulations on procurement. We can do things more quickly and with more flexibility. There's a very interesting book on this early work. James Webb, for whom the telescope was named, was the second administrator of NASA in the 1960s. Mr. Demling was his lawyer, the general counsel of NASA. But this shows you that to make these developments come about, we need contributions from all different disciplines, not just astrophysicists, not just engineers, not just technicians, but lawyers, administrative professionals, international negotiators. It's all necessary. So we will see if this interesting little movie will play. This is the James Webb Space Telescope while it was in our clean room for testing. There's not too much sound. If you see it, it is rotating slightly. This was in our clean room at NASA for just a few weeks in this configuration, and it was quite the thing to take a look at this firsthand. So what do lawyers do for projects like this? Well, it's our job, my job, to help us get from the beginning of this project to the end of the project without any distractions, such as lawsuits and other problems that come up along the way. So our client, the world famous scientist, can focus on the science. But you know what? Lawyers are interested in science too. Non-specialists are interested in science. And for a public project, that is absolutely essential. On the lower left, as an example of this, I was in Milan, Italy, 2 years ago on vacation. Very interesting city. My wife and I came to a newsstand the day after the first science results were announced from this wonderful project. I had on my project shirt, you can see in the picture, and we saw in the newsstand, every newspaper virtually had headlines about the first science results from this project. It is really a wonderful thing. I almost had to cry. So we also have many interesting clients along the way. NASA lawyers, we have to make sure that different awards and prizes can be accepted by our scientists. The standard is given on a regular basis according to written standards. One of my clients long ago got many prizes, one every few months, and it became very interesting. He wrote a book called The Very First Light, The Cosmic Background Explorer, COBE, and the Cosmic Microwave Background. And this book is still in print. The author is John Mather. He was my client. In 1996, he published this book. As a result of his work, Stephen Hawking described it, seeing the differences in the background radiation of the universe as the greatest discovery of the century, if not of all time. Well, that makes you wonder, well, this could be a very interesting subject. In 2006, as a result of this work in the late 1980s, Dr. Mather, my client, received a Nobel Prize in physics. So this is a good topic, and if you ask Dr. Mather, it is ripe for other Nobel Prizes to come in the future. So how are we doing making progress on the goals of this wonderful telescope to find the first stars and galaxies? Well, it's getting very interesting. My favorite story, we are finding galaxies older and older towards the beginning of the universe. My favorite is Maisie's galaxy. Why is it called Maisie's galaxy? You see a picture of it enlarged in the lower right-hand corner, just a little red dot. This was published in March of 23, just over a year ago. It's really quite recent, as part of the Cosmic Evolution, I will get the acronym wrong, Cosmic Evolution Early Release Science Program, SEERS. This is really just to see what the telescope can do. It is not even the focus study, but they found this one. Z, I'm sure many of you know, is a measure of redshift, quite high number, corresponding to only 390 million years after the Big Bang. That is 97% of the age of the universe. We are very close. Why is it Maisie's galaxy? Well, it has an interesting story. We all like to know our origins, our childhood when we were a baby. On the left is a picture of your presenter today holding his son reflected in the mirror of the James Webb Space Telescope. This was really a surreal experience for me. I hope he will appreciate in many years to come, because his view of the universe will be completely different than the one I had growing up. But speaking of young children, on the right is one of our researchers. This is Dr. Stephen Finkelstein with his daughter. So Dr. Finkelstein spent many years away in the laboratory late at night, away from his family. He found this particular galaxy, Maisie's galaxy, on the day his daughter was born, Maisie. And she said, "I always wanted you to name a galaxy after me." So right now, one of the oldest, farthest galaxies we have ever seen in the universe is Maisie's galaxy, named after Maisie Finkelstein, and she is now very famous 12-year-old. But what about our progress on this second goal, to look at some of these interesting planets? This is, to me, really the most interesting aspect, because it touches on the fundamental questions of our life. Is there life elsewhere? Well, I'm sure many of you know we discover planets indirectly. Right now, it's very hard to see them in visible light through the transit method and the wobble method. But with the transit method, I'm sure many of you know, we subtract out the spectrum from this system of star and planet, and we can learn quite a bit about the planet. And this is for stars nearby in our galaxy, but very far away from us. Just last year, we found this interesting spectrum. It's probably the only spectrum that you will see a lawyer presenting, but it's quite significant. WASP 39b is an interesting planet. And the spectrum here shows the presence of many interesting things that we see here on the Earth, including carbon monoxide, carbon dioxide, and water. This is an interesting planet, but it's 1200 degrees, Fahrenheit, very hot. So it's not liquid water, about the size of Saturn. It goes around its star in 4 days. It's a little different than our system. This is 700 light years away, but this is one of the early spectra from interesting planets that help to show us conditions that might be quite similar to planets that we know, but it gets even better than this. And I almost have to check the results every week. The most interesting one we have found so far, and this is a spectra of its atmosphere. That is how precise this instrument is. It can tell us a little bit about the atmosphere of an extrasolar planet. And what do we see in this planet? K2-18b. It's very famous. We see some interesting compounds such as methane and carbon dioxide. But you know, these can be produced by sources other than living systems, such as volcanoes. But there is a very tentative finding. On the right, you can see some spectral lines for the molecule dimethyl sulfide. This is a very famous compound. I am not a chemist, but if you want to have a good cocktail party conversation, you can start talking about these two words. That is a compound that is produced only by plankton on the Earth. There is no other source. And we see it in the atmosphere, perhaps, of this extrasolar planet K2-18b. It's 120 light years away from Earth. It orbits a red dwarf star. So plankton are quite important on the Earth. They're producing this dimethyl sulfide and a lot of other things. We're not sure about this. We need some more data. It's very difficult to make a follow-up observation the next week after you make your incredible discovery, because everybody wants time on the telescope and you have to compete again to get more time on the telescope. But stay tuned, because if it's not this one, These days are coming. I'd like to take a big picture view of this international science project. You know, there are a lot of difficult things going on in the world. Human beings do a lot of bad things to each other, but we also do some good things. And this is an example of that. It helps to inspire us to be better human beings, to learn our place in the universe. And if your project is successful, it becomes part of popular culture. I went to the post office last year to get many copies of this first day of issue stamps, including this wonderful project. Of course, it doesn't look like this in space now, but we will excuse the artistic license. So that is an introduction to this wonderful project, wonderful international science project. And I will just pause now for some questions if anybody has some.
Thank you, David. A very good presentation. Now the questions. Who want to be the first?
Meanwhile, I try to make my screen a little bigger so you can see your presenter as a human being. There we go. Okay.
Right. Well,
So it's fascinating to me to see all of you from all these different locations come together at this time to talk about this project.
I have a question. How long is supposed to last this telescope?
That is a good question and a very interesting answer. It was originally supposed to last 10 years.
10
But
years.
because the European Space Agency has put the telescope in so precisely the right spot, we think now it will last 20 years or more. The technicians that worked on this project produced the launch vehicle on an assembly line, one every 6 months. Of course, now they're working on Ariane 6. But they said, you know what? We do it all the time, but we know some launches are special. And they did such a good job for us that we have to use a lot less fuel to maintain the position. And this has extended the life of the telescope almost double. So thank you, Isa.
And after this telescope, are there a replacement planet, or it's not the does the decision change? That's to say. Do you have a replacement in mind?
Yes, of course, this is what makes the topic interesting, especially to all of your students who will have their careers in the coming years. We are now working at my center on the Roman Space Telescope. It's not like James Webb, it's not infrared. It's a visible and ultraviolet telescope, very similar to Hubble Space Telescope, but it is a very wide field of view. And we will look for changes in the sky over time, very important. Beyond that, we are in the very early state. That will launch in 2026, I think. Beyond that, we are working on early concepts for the successor to James Webb called the Habitable Worlds Observatory, HWO. The international science community is recently developing consensus this is the right instrument to build. Very expensive, extremely precise, 10 times better than James Webb Space Telescope because it will have a coronagraph on board to block out the light of the star. And we should be able, with that instrument, to take visible light pictures of extrasolar planets. And I think if James Webb does not find signs of life before that time, this instrument surely will. But the message for all the students is there is always a wonderful science project in development. The ones on the ground are closer to you. They need all kinds of people to help them succeed. And of course, the space telescopes and ground-based telescopes are complementary. We need both of them. So it is really a golden age of astrophysics. We wish it was a golden age of funding, but we are working on that, and that's why it's important to have all these international contributors.
Well, thank you. Are there any speculations about future manned missions for repairing this kind of instruments? Not this. We know that the James Webb is in Lagrange point, well beyond Earth's orbit. But of course, it can be repaired in the same way that the Space Telescope was repaired. There are no space took for reaching this telescope. But in the future, are there any speculation about long distance manned missions for repairing this type of telescope?
It's a good question, and this was a very robust debate when the telescope was being planned. Where should we put it? If we put it in low Earth orbit, similar to Hubble Space Telescope, we can get to it and fix it. If we put it at the Lagrange point, we can't get to it, at least not right now. We could not get to it with the space shuttle. We have no capability in human spaceflight now to go to James Webb. It's too far. Maybe someday we will. There are disadvantages to being in low Earth orbit close by. Half of the orbit, you cannot see anything because you are blocked by the Earth. On the other hand, Lagrange point is stable. You can observe all the time, 24/7, but you can't get there. So we would like to have some capability to service even the James Webb Space Telescope or future space telescopes. And maybe someday we will do that. The human spaceflight part of NASA's budget is very expensive. It's more than half our budget. And we do not have at present universal support to develop this deep space human spaceflight capability. We are working on it. Right now, there is the Artemis program, and that has a goal to put human beings on the moon. But the Lagrange point is 3 times farther than the moon and very difficult to get to. So these are interesting discussions to have about space telescopes in the future. And of course, we can also make much bigger telescopes through the use of interferometry. There are some proposals to put one telescope like this at one part of the Earth's orbit, then 6 months later, put another one at the other part of the Earth's orbit and have them work together. This is a technological challenge. But the future is very bright for all these concepts, and we need international consensus and international funding. But yes, we would very much like to go and be able to visit and fix problems if they develop. Right now, the Hubble Space Telescope has only 2 gyroscopes operating from the original 6, and they are failing in a predictable fashion every few years. We could previously just go and replace them with new ones, but we don't have the space shuttle right now, and we don't have any capability for EVA, extravehicular activity, to work on Hubble. So it would be nice if all of the international participants developed some consensus to do this. I think eventually it will happen. And then we will be able to go work on our telescopes, just like you go fix your car.
Well, thank you. The future looks promising. Okay.
Hey, I got a question about the instruments of James Webb Telescope. What do you think that, or which instrument you might think that has more room of improvement for the
Ah,
next James Webb or the next infrared telescope?
that is an excellent question. Which instruments have the most promise to be developed? And the answer is all of them. But I will just say this. The media reports all the pretty pictures from this telescope. They are interesting, but they are not the things of most significance from this telescope. The most significant things from this telescope do not make pretty pictures. Well, maybe. They show a spectrum for a planet far away from our own, and they show a spectrum of the host star. We can figure out, is it an appropriate type of star, an appropriate type of planet? We find 5,000 or 6,000 planets so far. The spectrometer instrument and near-infrared camera are most interesting to me. These can all be improved with better versions, and we need all kinds of people to work on this. We need the technicians to build it. We need the engineers to design better instruments. And I'm very optimistic we will have much better instrumentation. It's always evolving.
So much.
Another question. People.
Hi, thank you very much. You mentioned a lifetime of 20 years or so expected now. I guess the infrared instruments work at ultra low temperatures as in Earth. And how will you keep those ultra low temperatures for 20 years?
It's a very good question. We think the telescope will last that time. The instruments may not, as you suggest. Much of the cooling is passive with the multi-layer sun shield. We expect that to last a very long time. It's also in a very cold place itself. And then we have some active cooling measures, which I am not an expert on, but these will finish very soon. And you are correct. Eventually, we will run out of resources to operate the instruments. They will still operate. They may not be as cold as we would like. You know, we are looking at objects very close to absolute zero across the universe, and these are very faint. So we tried to keep the telescope as cold as possible, as long as possible. You know, when we were testing this telescope at my center in our thermal vacuum chamber, the engineers normally cool things in the chamber to temperature minus 200 something with liquid nitrogen. But it was not cold enough to test this telescope. So we built a container for liquid helium to put inside the container of liquid nitrogen to test this telescope. And that application will continue. It's always a continuous challenge to make the instruments better and the telescope better and to last a long time. But really, to answer your question, is we would really like to go to the telescope to visit it and make repairs and improvements. You know, Hubble Space Telescope was designed from the beginning to be modular, meaning it has compartments. You just slide your old instrument out and you slide your new instrument in. It worked really well. And the astronauts made 5 visits to the telescope. But, you know, that is about 380 miles, forgive me, above the Earth in low Earth orbit. It is not 1.2 million kilometers away, but maybe someday we'll have highly trained astronauts to go visit the telescope and replenish some of the coolant to keep it cold.
Another question. People at the net. If you want to write, I read for David.
Let me just say in closing then, I envy you at the start of your careers. The future for world-class international space science and ground-based science is extremely bright. And maybe I run into you at some international conference, like I ran into Julia. And so we can have this wonderful international exchange. And I thank Dr. Campari for facilitating this for us today.
Well, very thank you then. It was a wonderful presentation. 3 continents. Well.
Thank you so much. Bye for now. Bye-bye, everyone.